All right. Hello, chemistry honors class, chemistry co-seated honors class. We have started our unit on IMFs, intermolecular forces, and I briefly have already introduced what a homogeneous versus a heterogeneous mixture is. Homogeneous means it looks like there's even distribution of particles. Another way we call it is we say it's a solution with a solute and a solvent, right? And then, of course, heterogeneous mixtures are obviously, you can see the individual components, okay? Sand and water, trail mix, salad, right? So what you guys are going to be asked to do now is dig a little bit deeper into the concepts of solubility, how things mix, and ways that we can affect how well things mix in a standardly homogeneous solution, right? So here's a big model that you need to know. The first is likes, dissolve, likes. So you guys have previously learned about molecular polarity, that certain molecules can be polar or non-polar. And what we mean by like, dissolve, likes is that polar likes to mix with other polar substances. They'll be soluble, they'll mix well, they'll become a homogeneous mixture, a solution you can't see or easily tell the individual components of. And non-polar likes to mix with non-polar substances, again, producing a non-polar solution, homogeneous mixture. So an example of this would be, think about, right? Oh my goodness, my color choices. Think about polar with polar. Think about how fats and oils. Oh, actually, you know what? No, that's actually a better example of non-polar. Fats and oils mix pretty well together. Okay, but when you mix oil and water, it doesn't work because water's polar, but oil's not. So what we say is that water with another polar substance like alcohol, right? Any type of alcohol, which by the way is totally how they did it in the Prohibition ages, right? They dilute the alcohol because no one could tell, no one could see the difference, right? So let me go back to my colors. Any form of alcohol group and water are two polar substances, okay? So we say specifically, I previously introduced, right, soluble versus insoluble, things that mix and things that don't mix. But when we specifically talk about liquid mixtures, we have a unique terminology. We say it is miscible if it mixes well, aka soluble. And we call it immiscible if two liquids do not mix well. Insoluble. This is just a specific subcategory of terminology that specifically holds the connotation or the innuendos or the nuance of talking about liquid mixtures. You could just say soluble and insoluble for two liquids mixing, but you would never say sugar and water are miscible because that's a solid plus a liquid. That's not what we want. Okay, so there's just like these little nuances of communication and chemistry. All right, so if you hear miscible and immiscible, your brain should be thinking, solubility between two liquids. Okay, so what is actually happening at the particle level when we look at dissolving molecular solids? Now, what are molecular solids? This goes all the way back to unit like 2 or 3, okay? Where a molecular solid can kind of be understood as a solid held together by intermolecular forces between individual molecules. Okay? And so what happens at the particulate level when we think about dissolving a molecular solid, such as sugar, sugar is a molecular solid. What we say is that what happens is that the sugar, or I could say the molecule to molecule attractions, okay, are broken and molecule to water attractions. Ooh, that's not going to fit. That is not going to fit. Attractions are formed. Okay. So what we say then is that the compound or the molecular solid has dissolved. The individual molecule units have formed new IMFs with the solvent, which is usually aqueous water, which is usually AQ, aqueous water. Okay, so how does this compare with understanding the solubility of ionic solids? Remember, ionic solids are held together through intramolecular forces known as ionic bonding. So here what we say is the intramolecular forces, aka the bonds between the ions, are broken and new attractive forces are formed between the ion charged and the polar water molecules. Now, automatically, your brain should be going like, wait a second. I can get behind molecular solids dissolving, right? IMFs being broken to form new IMFs. I can get that. But what the heck is going on with breaking ionic bonds, intramolecular forces, and forming intermolecular forces? Like, what's happening there? Well, this is kind of a unique subcategory of IMFs because normally IMFs only involve breaking IMF to IMF, right? Normally it involves breaking old IMFs and forming new IMFs. But what's unique about ionic solid IMFs in specifically water? Okay, so what's unique about ionic compounds in water is that we see an ionic bond break to form new IMFs. Okay. How do I write that a little bit better so it's even easier to see? Is that, let me do it in a different shade of blue. Maybe that helps you. Is that we see old ionic bonds break to form new IMFs. Okay. We call this very unique type of IMF that can only be seen with ionic compounds, dissociation. The ions, we say, dissociate in water, which means in the ions are split and surrounded by water molecules, okay, where they form what we call ion dipole interactions. Ion dipole interactions. So what we say is that the ion, say, let's say a cation and an anion, okay, start off together. And what happens is they begin to break apart. Their intramolecular ionic bond breaks. And then what you get is, and by the way, you have a bunch of water molecules around here. And I'm going to draw water like this, actually. Water is going to be drawn where I have oxygen and then 2 hydrogens attached to it. What happens in water, it breaks up in water, and the individual ions split up, breaking ionic intramolecular forces. And that was the wrong color. Okay, minus. And then what we say is the polar molecule of water then orients around itself, creating what we call hydration shells. What we say is hydration shells form using ion dipole interactions. And so what that means is literally what it says. It's an ion plus a dipole, polar molecule of water attraction forms. So your water will form surround the cation, so it's more negative oxygen dipole, partial charge, okay, is oriented near the cation. And then for the anion, the surrounding water molecules will orient itself. So they're more positive dipole, partial charge hydrogens in that molecule are closer to the anion. And so what you see is you literally see, zoom in, okay? You literally see an attraction between the partial positive end of the water molecule, polar molecule, with the negative cation, right? This is your partial positive end. An ion to a dipole interaction. And for your cation, ooh, where is my mouse? Hold on. Did it just die on me? Oh, gee willikers. For your cation, and 1 second, guys, my pen just died on me, so let me switch out pens. Let me turn off my settings, and Bluetooth is off. And now I go to my emergency backup pen. What we're seeing for the cation is similar but opposite. The positive cation is being surrounded by the negative, partial negative region of the polar molecule of water, and the more positive regions away from it. And so what we have is the partial dipole, partial negative end orients itself around the cation. And this happens throughout the entire water. By the way, this explains why swimming in a pool is so dangerous. Chlorine ions are floating free in water, completely dissociated, broken up into their individual ions, now being surrounded by a hydration shell, of water that has oriented itself through ion dipole opposites attract, okay? And now what you have is a bunch of charged ions just loose in water. And so when lightning comes with an electric current, it's literally just like a stream for your electricity to run through. This is why you should not be in water, chlorinated water, especially during a lightning storm, because you have all these loose ions that are dissociated in water that are basically just like a tunnel, a magnifying tunnel for electron currents or electrical currents, charged currents. Okay. So that being said, let's look at factors that affect solubility of specifically solids in liquids. Okay, so let's turn our attention from analyzing previous types of solids to now just general solids. Okay, so here's the goal when we talk about increasing solubility. Okay, the goal here is the point of our discussion is goal. How do we increase solubility? Okay, so that's what we're analyzing here. So what we say is that what we need to consider is it's really all about collision. Collision. Okay, oops, I think I misspelled collision. All about collision. Why is this pen is not as good? It's one of the Amazon cheap pens. All about collision and interaction between particles. So all of these methods I'm going to provide to you of factors that we can use to increase the solubility of a solid in a liquid is totally various ways that we can increase collision between the particles and therefore interactions between the particles. So the first way is by increasing the surface area. Okay, so you can crush or grind your solid. Okay, which means instead of having a big chunk of solid that your solvent particles suddenly have to fight through to get access to, what you're doing is you're making, instead of having this dense concentration of solids that your other particles are going to try to get to, instead what you do is you're spreading them out, okay, so that you get more easy access to interaction from your other particles. Let's put it like your purple particles. Okay, they can get quicker interaction with your solute or whatever solid you're dissolving in, you're trying to mix together. So that's kind of one way you could do it. You could also simply increase surface area by literally just working with a larger container, right? So you could also do it simply by using a larger container, a larger and specifically wider, using a wider surface area container, performing the mixture in a wider surface area container. Surface area container, right? So why mix two things together in a really tall, narrow cup when you could just mix it in a big old platter? It's really going to increase the likelihood of those particles interacting. Factor number 2, okay? You can simply agitate it more. You can increase collision through stirring. Okay, through stirring. So have you ever like mixed, I don't know, coffee and sugar together? Why is my pen not registering? Coffee and sugar together. And you're like, oh, this is taking too long. I'm going to stir it. Well, why do you think that works? Why do you think that speeds up the solubility process? Why do you think that speeds up the rate at which your two particles mix? It's because by stirring, you've actually increased the collision and the interaction between particles. Increased collision through stirring. Oh my goodness, this pen is killing me. Increased collision through stirring, right? An external force. An external force. Okay? So, the last way we can do this is through temperature. Remember that temperature is a measure of, why is this pen not working? Temperature is a measure of, oh, my pen's dead? Is a measure of kinetic energy. Hold on, guys. I'm struggling with my pens. Give me a second. So if temperature is a measure of kinetic energy, by increasing the overall kinetic energy, okay, by increasing the overall kinetic energy of the sample, you're increasing the speed at which the particles are moving. And if you increase the speed of the particles moving, you are going to also, as a result, increase the likelihood that they're going to collide. If you increase the likelihood they're going to collide, you're going to increase the chances that the particles can mix and therefore increase solubility. Sorry, guys, all my pens are dying. Give me a hot second, okay? So let's see if I can get really lucky and get one last pen connected. All right, give me 1 second. I'm going to pause this for a second and then I'll resume it once I get my pen situation figured out. Okay, so temperature is a measure of kinetic energy. So by increasing temperature, you increase the energy of the particles. Okay, therefore, you increase the percent or possibility, of collision. Oh my goodness, my handwriting is just really struggling right now. Increase the possibility. Whoa, of collision. Possibility of collision. And then, of course, that means the more you collide, the more your particles interact, the more likely and better chances you are going to be able to mix a solid particle with its new liquid solvent particles. Okay. Quick note about temperature, by the way. I don't know if I've introduced this to your class yet, but there's another unit for temperature known as Kelvin. In science, it is usually preferred to use Celsius because that is the international unit for temperature. We Americans just decided that apparently we're not using Celsius and we're using Fahrenheit, which no one else in the world uses. Okay. But there's also one more unit, and that's known as Kelvin. Kelvin is a unit that I'm going to talk about later in Unit 6 when I talk about thermodynamics and why we even have it. But essentially, what you need to know is that I can talk about temperature in terms of Kelvin. And by the way, it's not degrees Kelvin. It's just like plain old Kelvin. And so if you want to convert between Celsius and Kelvin, you should know that Kelvin is equal to whatever the value of Celsius is plus 273.15. And that gives us the temperature in this new unit called Kelvin. So, honors, you should be able to describe, okay, one, when a liquid is miscible or immiscible. You should be able to use that terminology. Two, when two substances based off of their molecular polarity will be soluble or insoluble. Three, okay, you should be able to explain the particle level of what is happening for a molecular solid versus an ionic solid. And of course, the unique intermolecular force of ion dipole attractions with ionic solids. And then you should also be able to be able to describe 2 to 3 ways that I can increase solubility between a solid and a liquid. Okay, and really remember, it's all about how do I increase, what are the methods of increasing collision and interaction between those particles. So that's what you guys should be able to do. There's plenty of, actually, I don't even think there's actually that many workbook problems. So you guys should be able to kind of whip out some workbook problems. I'll check in on you guys soon, but you will be tested on this on the next assessment. So be prepared with any questions you have. Try out those workbook problems. Look at the optional video I provide on the Weebly website, and best of luck to you all. Good job, you guys.